I intentionally drew, like, I could have just drawn this picture originally, but I intentionally drew it like this in like some suggestive way where it's like on a circle, because it is true that, like, if you do this times 2 mod n operation, it rotates this circle like one step. It rotates it like 1/11 of a circle. And maybe that sufficiently motivates to you the plan for us, which is the following. Yeah, let's write R for the unitary operation associated to this quantum code that we just made times 2 mod n. And the plan is to do rotation estimation on R. Okay, that's the whole plan for how we're going to do step 1 efficiently. Now, what does this get at? Like, ideally, you want to kind of like say, like, oh, R is like rotating by 1/11 of a circle. So maybe we can figure out 1/L, and then we'll take the reciprocal, and we'll figure out L. It's actually kind of like that, although more subtle. Okay, before we do that, we have to get some, I don't want to say technicalities out of the way, but we got to talk about all this business of rotation estimations, number of digits of precision. Okay, so we're going to want to, when we do rotation estimation, like especially if you think about like, oh, we're going to try to get like 1/L out of it. I mean, 1/L is like a fraction where like the denominator has like thousands of digits. So we're going to need thousands of digits of precision in this rotation estimation. But we're prepared for exactly this circumstance through all our previous hard work. Because we know that, I mean, normally you can't get like thousands of digits of precision when you do rotation estimation too easily. But you can do it if you happen to have efficient code, not just for R, but also for like R to the 10 and R to the 100 and R to the 1,000 and so forth. And good news, we do have that code. So we have efficient quantum code even. Let me just say code, and I'll talk about it in words. Code for all these things that we need, like R repeated 10 times, R repeated 100 times, R repeated, I don't know, 200 times, or not 200 times, 1,000 times, let's say like n times, 10 to the n times, because, well, what does it mean? What is R 10 to the k? This means repeat R for 10 to the k times. But what is R doing? It's just doubling mod n. So it's like, this means like double a number 10 to the k times. So it means like do times 2 10 to the k times. It's all mod n, which is equivalent to like multiply 2 to the 10 to the k mod n. But for any particular value of k, like 1, 2, 3, 4, 5, 6, etc., we can on the side like compute this efficiently with modular exponentiation. Which again, I hope you remember about. If not, we'll remind you later. So even if like, k is like 1,000, there's like an efficient algorithm for computing 2 to the 10 to the 1,000, 2 to this like 1,000-digit number up here, mod this other 1,000-digit number. That you can do efficiently. And therefore, like, the classical code for this is just multiplying by this enormous number that you can easily figure out. You also have to figure out its inverse. And then in the same way you got the quantum code for R, you can get the quantum code for R, repeated actually any number of times. It doesn't have to be a power of 10. So this is like a key part that we don't just have quantum code for like, doing one step along this chain. We have quantum code. You can actually get quantum code for doing like any pre-specified number of steps along this cycle. And rotation estimation wants like, powers of 10. And because of this, when we execute this plan and do rotation estimation, we can get basically as many digits as we want efficiently. Like if you want 1,000 digits, like that takes like 1,000 applications of R. If you want 2,000 digits, you can get 2,000 applications of R. So we can get basically as many digits as we want. Precision. And I'll just tell you as an aside, if you're trying to factor a 1,000-digit number, then in the key quantum subroutine, when you do rotation estimation, you'll request 2,000 digits of precision. Or if you're trying to do a 5,000-digit number, you'll request 10,000 digits of precision. So the number of digits of precision we'll eventually need, as we'll eventually see, is like twice the number of digits of the number you're trying to factor itself. Okay. So that's the plan. We have the code for R. We also have all these codes for R to the 10, R to the 100, R to the any power of 10. And the plan for trying to figure out L, the length of this cycle, is going to involve doing rotation estimation on R. Now we have to ask ourselves, why is this going to help? Well, let me now tell you what I'll call the crucial fact. And a lot of next lecture will be about proving this crucial fact. But I'll just state the crucial fact to you now. So R is unitary. So in addition to being like, in the case n equals 21, like the quantum operation that turns this into this, into this, into this, into this, into this, back into this, it's some kind of rotation on, in this case, 32-dimensional space. It's some kind of high-dimensional operation. So it has these, 2D planes of rotation associated to it. And the crucial fact tells you about them. It's that the 2D planes of rotation for this R well, we're going to see what they are, but I'll just tell you now what their angles are. Have rotation angles. There's lots of them, like lots and lots of them, but their angles are 1 over L times tau. Remember, tau means one full turn of the circle, which is 360 degrees. And 2 over L times tau, and 3 over L times tau, and L minus 1 over L times tau, and also 0. So it has all these planes of rotation. And technically, I guess I should say for R restricted to just the stuff spanned by the basic states on the cycle. But anyway, we'll get into that comment later. Yeah, they have these as the rotation angles. So it's like 1 over L fraction of the circle, 2 over the L fraction of the circle, and so forth. And that really is kind of to do with the fact that like this cycle picture I deleted, like what are the symmetries of the cycle? You can rotate it 1 notch or 2 notches or 3 notches or L minus 1 notches or 0 notches. Like somehow the fact that those are the symmetries of the directed cycle graph is the reason why like these are the angles of rotation for the different planes that R rotates. And technically, the 0 means it's like not actually a plane of rotation, but it's like a single direction where it's not doing anything. That's a minor point. Yeah. So that seems maybe cool because let's say, for example, you could somehow figure out how to make some qubits in a quantum state whose vector was in the 2D plane of rotation that rotated by 1 over L fraction of the circle. Say you could somehow do that. Then you run rotation estimation. It gives you like as many digits of precision as you want of 1 over L times tau. That's 2 pi. You divide by that, and you've got a great approximation to 1 over L. And then you take the reciprocal, and you've got L. So that would be awesome. And that's almost how it's going to work. But it's more complicated. Because, rotation estimation, you need the ability to do R and maybe also its powers. But you need like a starting vector, a starting state. And unfortunately, we don't know how to get a starting vector, a starting state for our qubits that's like in any particular one of these 2D planes of rotation. These are these like perpendicular 2D planes of rotation. And basically, the only thing we're going to be able to like know how to do is take like basically this vector, this basic state that corresponds to 1, which is the only state that we're sort of sure is like in this cycle. And it will have different amounts of projection onto all these 2D planes. So let me just write another fact that we'll have to prove next time. That if we do rotation estimation with qubits in the starting state, which is just the one corresponding to like 1, the binary encoding of 1, it turns out, and we'll prove this next time, what happens is that we'll get an excellent estimation of a uniformly random one of those angles. Okay, and we won't actually know which one. So the effect is going to be that we make this, our qubits in this state, we do rotation estimation, and basically rotation estimation will print out a random one of these angles. It's kind of like making our life harder than we hoped. We were kind of hoping it would just print out like maybe the first one, like 1 over L times 2 pi. And then we'd be like, great. But now it's going to print out a random one of those angles. But that's going to be just good enough. So conclusion. Okay, so these two things we're going to like talk about in the next lecture. But now I'll write the upshot of these two things. The upshot is there's an efficient quantum algorithm that prints out, with overwhelming probability. I'm really kind of ignoring that stuff. As many digits as we want. So maybe like 2,000 digits if we're factoring a 1,000 digit number as desired of k over L. Whenever we get out the angle from rotation estimation, we're just going to immediately divide by this tau. We'll immediately divide by this 2 pi and just get back the fraction. So we'll get as many digits as desired of this fraction, k over L, where k is a truly uniform random number between 0 and L minus 1. Okay, so this is like the quantum part of the algorithm. And that's what we'll focus on really understanding next time. But for the rest of this lecture, we're just going to take this conclusion for granted. So we're factoring capital N, and we make this code for times 2 mod n, and we turn it into quantum code, and we get the quantum code for all these powers. Then we make a bunch of qubits, and I don't know, if like 1,000 qubits, and we like toggle the last one to get into this state. Then we give that to rotation estimation with this R for times 2 mod n and all its powers, and be like, just give me what you give me, and it'll give you tons of digits of precision of a random fraction with L in the denominator. We're like, man, I wish you told me L, because if you told me L, then I'd do those last 2 steps of like figuring out x 2 to the power of L over 2, and then doing the GCDs, and I'd be done. But it only gives us this. So I'm going to call this, I'll call it a clue, because it's like a clue to what L is. And the question is, okay, it's all this quantum work, which gives us this, it gives us like a clue about L. Is that good enough? Can we find L? And the answer, happily, is yes. And this is more number theory. It's like more easy-ish number theory, which I'll illustrate to you today. But the point is, you do all that, you get this random fraction. Like you get like zillions of digits of this random fraction, and that's a clue. And then you do it all again. You do the whole quantum rotation estimation thing again, and you'll get a different random fraction, k over L. You'll get a different clue. So now you have like 2 fractions that are both like random fractions with L in the denominator. And you can do this as many times as you want. I mean, subject to efficiency. You can do it 3 times, 4 times, 5 times, 10 times, and collect up like a bunch of clues in the forms of these fractions. And what I'm telling you is, with a few clues, there's a classical algorithm that figures out L with overwhelming probability.